Hi there. Last time we have shown by a numerical example how the speed of reaction and the order of the reaction determined theoretically can be so different from what is observed in practice. For example, if we assume that the decomposition of ozone to oxygen goes this way, where we take two ozone molecules to produce three molecular oxygen molecules, then we'll have the speed of reaction determined by the speed constant times the initial concentration of ozone to the power of 2, because here 2 is the stoichiometric coefficient. So the order of the reaction will be 2. However, if we consider that the reaction proceeds this way, where we really need only one ozone molecule to produce one oxygen molecule and an oxygen radical, then the speed of kinetic reaction would go this way, where we have the first order reaction. First order reaction indicates only one molecule is needed for the reaction to proceed. Order of reaction of 2 assumes that we need two ozone molecules to collide for the reaction to proceed. However, we have shown that in practice the mechanism of decomposition of ozone into oxygen, it really takes in two steps, and first is an equilibrium step, or the oxygen plus an oxygen radical is produced, but this reaction is very reversible. The equilibrium is achieved rapidly, and only the second step reaction, where this ozone reacts with an oxygen radical, then it forms two oxygen molecules, and this is really the slow step for the reaction, which is also determining for the reaction to be completed. Now, we also show that the kinetic law, now it looks completely different, because the slowest rate determining step of the reaction is what determines the kinetics of the reaction, and in the end the order of the reaction. So in this case we will have a reaction order of 2, obviously, and the kinetic law that is looking like this. Now we are going to take yet another example that is hopefully also very revealing, and that is the decomposition of nitrogen pentoxide into nitrogen tetroxide, dinitrogen tetroxide plus one oxygen molecule. Experimentally, it's determined that the reaction kinetic law for this reaction is minus the decrease in the initial concentration of the reactant over time. That would be equal to Kn2O5 at the power of 1. So this is in experiment what has been shown. Now, obviously, because I wrote the reaction like this, theoretically I would have written that the V is Kn2O5 to the power of 2. That means N would have been 2, which suggests that I needed 2 molecules of dinitrogen pentoxide to react in order to form these two products. The experiment has determined that the reaction, the composition reaction, really takes in 3 steps. The first step would be an equilibrium reaction, where we would form NO2 plus NO3, and this equilibrium is rapidly attained. So this is really the step 1. In step 2, this NO3 that is produced here is a radical. In the second step is NO2 then reacting with NO3 radical to produce NO plus oxygen plus nitrogen dioxide, and this is slow. In the third step, we would have really the reaction between nitrogen monoxide plus nitrogen trioxide radical into for the final product. And this is also fast. Obviously, if I sum up the reaction, I will end up with the reaction, the final reaction that we have here. Now, because this is the slowest reaction, would be also the rate determining step. They usually called rate determining step. And this will give me the kinetic law. That means the speed of reaction would be K times NO2, the concentration of NO2 times NO3 radical. But how do I get from here to here in 2051? Well, we see that we can calculate the concentration of NO2 and NO3 that participate in the slowest step from the first reaction, which is an equilibrium reaction. So therefore, if we write the equilibrium constant for the reaction 1, because it's an equilibrium process, then we'll have the product of products, NO2 times NO3, divided by N2O5. Now, the multiplication, the product between the concentration of products is nothing else than NO2, NO3 radical is equal to K, the equilibrium constant of the first reaction, times the concentration of N2O5. So then we can replace this value in here, this value in here. So we get the speed of reaction is K times N2O5. But because these two, the product of these two is always a constant, we can write now V K prime, the concentration of N2O5. And there you go, the demonstration of the kinetic law of the reaction. If I know the mechanism of reaction, if I know which is rate limiting step, so we'll get to the value of the rate equation and the first order that we observe here, which is different from what we would have written if this was just purely theoretically determined from assuming that this is one-step reaction. I hope this was useful. Thanks for watching. Until next time. Bye-bye.